Good afternoon and welcome to today's webinar titled Parametric EM Simulation. My name is Arvind Krishnan and I will be your presenter today. Let us start with the agenda for today's presentation. I will start by giving you a brief overview about EMWorks, its products and its applications. Next, we will look into the different types of parametric simulation we can perform in EMS. I will also show you 3 examples using the product. Finally, I will conclude and answer any questions you may have. At any time during this presentation, you can ask me a question by simply typing it in the chat window. I will answer all of those towards the end of this presentation. We will start with a very short note on EMWorks. EMWorks is a CAD embedded simulation company. Our products, both EMS and HFWorks, are gold partner products to SolidWorks, and hence EMWorks products are the #1 choice for electromagnetic simulation for SolidWorks users. As I mentioned earlier, we have 2 different products. The low frequency electromagnetic simulation product is called EMS for SolidWorks, and this will be the product that I will focus on today. We also have a high frequency electromagnetic simulation product called HFWorks, and if you're interested in this product, there are videos and webinars related to this in our website which you can view them. EMWorks products are trusted by over 500 customers worldwide, and they are the #1 choice for electromagnetic simulation for SolidWorks users, mainly because the look and feel and the ease of use of the product makes it extremely easy to learn, and hence you can become productive very quickly with the EMWorks product if you're a SolidWorks user. Now let us take a look at the products and bundles that we offer here. EMS has 2 main bundles. One is called the EMS Professional Bundle and the other is the EMS Premium Bundle. Now the EMS Professional Bundle comes with 6 different solver modules. It's the electrostatic, electric conduction and AC electric, which form the electric modules, and the magnetostatic, AC and transient magnetic, which form the magnetic modules. Now any of these modules can be purchased separately, and they also come with several add-on options that allow you to do multiphysics EM simulation. You can couple your electromagnetic module to a thermal simulation to do a coupled EM thermal analysis. You can couple it to a motion simulation to do a coupled EM motion simulation, and finally you can also couple it to a structural simulation to actually do a coupled EM structural simulation. And the EMS Premium is a package that contains all of these, and it also contains this parameterization, which we will talk about in today's webinar. Regarding the HFWorks product, it is a product that is designed to do passive RF and microwave components. There are 3 different study types: resonance, S parameters and antenna studies that are possible in HFWorks. Now let us take a look at product-wise applications. Now towards the left you see this low frequency or electromagnetic simulation package, which is called the EMS for SolidWorks, and basically this package can do the following, and it can cater to the following industries and applications, starting from electromechanical type of problems where one can do with linear actuators, rotary actuators, motors, generators, solenoids, loudspeakers, magnetic devices, levitation devices, etc. And the key industries span across automotive, transportation, aerospace, and even consumer products. Then you can get to some electromagnetic applications where you use coils, you can use permanent magnets, and a combination of both can be used to design sensors and probes for NDT applications and so on. In the space of power electronics, EMS can be used to design and understand the behavior of transformers, inverters, bus bars, inductors, etc. Regarding the high frequency product, basically which caters with RF and microwave components, especially passive components. One can design antennas, multiplexers, couplers, etc. with this product. And one can also test for signal integrity, EMI, EMC type of applications as well. And basically these applications range around Internet of Things, aerospace, high technology, and nowadays even in the consumer goods application. There are two major types of parametric simulation inside EMS. One can have any geometry related information as a parameter. For example, if you look at the figure that I have on the right hand top corner, I can have a parameter such as the distance made in SolidWorks. So a distance made can be a distance between two components, and you can use that as a parameter. Okay, so any dimension variable in SolidWorks can be set up as a parameter. Once you define a parameter, you can study how your electromagnetic results vary with different values of the parameter. The second kind of parametric simulation is using simulation variables. Example can be the value of a current through a coil. In the bottom right image, you see a linear actuator which is actuated through a coil. Now the current that is passed through the coil can be used as a parameter. So this way, even with the simulation parameters, one can study how your electromagnetic results will vary with this parameter. Again, as a recap, any SolidWorks dimension can be used as a parameter in EMS, and also any simulation variable, for example, current, number of turns, mesh size, frequency for AC simulation, etc., can be used as a parameter. And as an output, any quantity that you can get out of your simulation studies can be studied with respect to the changes in this parameter. Next, we will look at three different examples which were solved using parametric simulation. In the first example, we have a magnetic arrangement which is designed to attract a steel plate. See, the objective of this simulation is to understand how the force varies with the gap, which is actually specified by a distance made in SolidWorks. To do this type of simulation, we set the gap distance as a parameter. And now let us take a look at this example using SolidWorks and EMS. So now I am in my SolidWorks simulation environment where I have modeled this assembly, and in this assembly I have a distance mate which is actually the distance between the steel plate and the magnet arrangement, as you see here. Okay, now we will use this distance mate as a parameter and do EM simulation. To do EM simulation, EMS is an add-in product inside SolidWorks, and hence by click of a tab you get access to electromagnetic simulation right inside SolidWorks. The first thing is to define a parameter. So when you define a parameter, you can select any SolidWorks dimension as a parameter. So in this case I have defined the distance mate, the distance between the steel plate and the magnet, lower surface of the magnet, as a parameter. Now once I have defined this as a parameter, now I can define various possible values for this parameter using the design scenario table. Now when I double click on the design scenario table, I can now see what are the possible values this parameter or this distance mate can potentially take. So for example, I would like to understand the force acting on the steel plate as a result of this magnetic arrangement when the arrangement is at several distances from the top surface of the plate. For example, when it is at a distance of 1 mm, 2 mm, 3 mm, all the way up to 6 mm, I would like to understand with what force this magnetic arrangement will attract the steel plate. Now, to be able to do such a simulation, we set up what is known as a magnetostatic simulation inside EMS, and we enable the parameterization. We define materials. So the top iron, back iron plate is defined as iron. And then we also have two magnets, N42 neodymium magnets, and the direction of their magnet direction is indicated by the arrow. So you see that the magnets are not directed in the same direction but in different directions so as to close the magnetic circuit. I also have a steel plate that is made of steel, and we have requested the program to compute the force acting on the steel plate. Now let us take a look at the results with respect to the parameters. So to look at the results, I can look at how the force varies as a function of parameter, and I can also look at the various force values here. So for example, when the distance between the two, the steel plate and the magnet device is about 1 millimeter, then I get a force of about 135 newtons. Now when I make the distance as 2 millimeters, I get 82 newtons, 3 millimeters it's 60 newtons, and so on. As you see here, the force does not vary linearly with distance, and we will be able to study that variation of force with distance using a parametric study like what I showed you here. You can also take a look at the results. For example, let's take a look at the magnetic flux density just from the front view, where the distance now is 1 millimeter. Notice that red regions in the top back iron shows you high level of saturation or high level of the magnetic flux density. Now when the gap is less, when the gap is more pronounced, say at 4 millimeters, you can see the maximum value of the magnetic flux density reducing a bit, but still the pattern looks the same. And about 6 millimeters, you can see this thing kind of thinning down, and also the force values are much lesser. In the next example, we will highlight how simulation variables can be used as a parameter. The objective of this particular study is to see how changes in the current affect the force acting on a plunger in this linear actuator. So we will set current as a parameter, and we will study how the force acting on a plunger varies with current. So let us dive straight into SolidWorks and see how this is done. So let's go to the solenoid example. This is a linear actuator, and we have several different components here. This is the coil, then we have the outer shield, then we have a moving plunger, and so on. So the idea of this linear actuator is when you actuate that by passing a current through the coil, there's going to be a force acting on the plunger. And now I would like to vary this current as a parameter and study how the force varies when I change the current. So as before, I go to the EMS tab, and here I have defined a study which includes parametric simulation. I have also defined the materials for the various components. For example, my plunger, and my other components, cover, etc., are made of steel 1010. Then the coil is made of copper, and I have defined what is called as a wound coil, where I select the components that comprise the coil, and I also select the phase through which the current comes in. You can see the arrows telling you the direction of the current, and here is where I set the current. I set in the number of turns of the coil and also the current. So this current value is going to be a parameter. So now, and I will request the program to compute the force acting on the plunger. Now as before, I go into the design scenarios, and then I look at the various values of current which can be used as a parameter. So for example, I want to vary the current all the way from 2.5 amps all the way to 6.5 amps in increments of 1 amp. So let's see what happens when I change from 2.5 to 3.5, 3.5 to 4.5 and so on. Now we can straight away go to the result plots where I can now see how my force value vary with my current. So for example, when I set in a value of 2.5 amps for the current, I get about 0.4 newtons upward force. On the other hand, when I have about 6.5 amps of current, I get about 2.34 newtons force upward. So you can see now how the impact of current variation is on the force. Okay. Now one can also take a look at how the magnetic flux density distribution is depending on the various scenarios. Here I have 2.5 amp current, and you can see the magnetic flux density distribution as a cross-section plot. And you can even read the values. You can notice that it's about 1.2 Tesla in the movable plunger. And versus if I go to say scenario 5 where I have 6.5 amps and I have a value close to 1.8 Tesla, and you can see the distribution of flux in the various components using a section plot. So let us take a look at the third and final example. This final example shows how the size of the magnet affects the flux density along a line at a particular distance from a Halbach array. So I have a Halbach array, and I actually have a line here that is at a particular distance from the Halbach array. And I would like to know how my flux varies along this line if I change the size of the magnets. The default size of the magnets is 1 inch cube. What happens if I reduce the size? What really happens to the distribution of flux along this line? Okay. Here, since we have cubical magnets, the length of the side is actually set as a parameter. So again, let's dive into SolidWorks and see how we can examine this problem. So here I have designed a Halbach array using SolidWorks, and you can actually see the magnetization direction for each of the magnets. And now we have to set the parameter. For example, when I design the cube, the length of the cube is actually made as a parameter. So to be able to do that, I go to the parameters folders as before, and the size of the cube is now defined as a parameter. It starts with 1 inch, but you can modify them. Now again, I go back to the design scenario in my study tree, and here I have the various different sizes that I've set as parameters. So I have 0.5, 0.6, 0.7 and so on. So as I vary the size of the cube, what really happens to my flux density along this line? That's really the objective of this simulation. So as before, I have created a study, and I've defined the material for each of my neodymium magnets, and I've also defined the direction. Okay. And now let's take a look at this plot. Now this is a plot which tells me what is the magnetic flux density along this line that I showed you, but at different values of the parameter. For example, if my cube was 0.5 inch in dimension lengthwise, this is what I get. This is the distribution of magnetic flux density along that line. When I make it 0.6, it's this with the, and then 0.7 is this scenario, 0.8, 0.9 at 1 mm is the scenario where I get obviously the maximum flux density distribution. So if your objective is to have a particular strength of magnetic flux at a distance from the magnet, but you have no idea what's the right size magnet that I need to choose. So you can do a parametric study like this and say, maybe all you're looking for is to have a maximum flux density of about 0.4 Teslas, and hence, 0.7 inch magnet would actually fit the role. So one can do these kind of what if scenarios using the parametric study in EMS. As before, one can take a look at the results. Now here is the distribution of magnetic flux in my model. I can look at it at various sizes, all the way from 0.5 inch all the way to 1 inch. Okay. Let's look at it from the back view, and you can see. So at various scenarios, we have studied the distribution of flux in the magnet, and in also the flux distribution along the line here. So let us go back to our presentation at this stage and get to our conclusion slide. As a recap, parametric studies in EMS helps you to study both geometry as well as simulation variables as parameters. We saw how any SolidWorks dimension, mate, etc. can be used as a parameter, and also we saw how any of the simulation variables, for example, we use current, can be used as a parameter. So this technique helps you to see how your electromagnetic behavior changes with different values of the parameter. And as I mentioned earlier, in the products and bundles, you can add parametric simulation to any of the above mentioned products and bundles. Again, on behalf of EMWorks, I thank you all for attending this webinar. I want to remind you that a link of this webinar will be sent to you shortly. Meanwhile, you can please visit our YouTube channel to watch our past webinars and also other product-related technical videos. I encourage you to download a trial version of our EMS product from our website. Here are some of our contact information and so on. So I look forward to seeing you in a future webinar. Now it's the right time to take a look at some of your questions, and I'll be happy to answer them. So if you have any questions, you can please put them down in the chat window. I already see a few questions, and I'll be happy to answer some of them.